Basin and Pamlico Sound. And before I get started, I want to acknowledge my co-authors on this presentation, Dr. Jack Kirky Fox and Gloria Putnam. And Gloria is from Sea Grant and Jack is from NC State University Bio and Ag Engineering. And I want to note all the partner logos at the top of the screen here. We're working with a number of partners on this project, including Sound Rivers, the Plastic Ocean Project, and UNC Wilmington. As you all know, we have tons of plastic. It's estimated at 8 tons per year that is escaping from coastal areas, especially coastal developed areas, into the ocean. There was a study that was completed by some European researchers that quantified how much of that is coming from rivers and not just directly from those coastal communities along the waterways, along the ocean. And they estimated between 1.1 and 2.4 million tons of plastic coming from these rivers, with 10 rivers contributing the bulk of that plastic. 2 of those in Africa and 8, by and large, the bulk coming from Asia. And as you know, larger plastics break down into smaller pieces or microplastics. And there's been several studies that have been trying to quantify some of these microplastics in our freshwater lakes and rivers, not just out in the ocean. So that's kind of moving upstream to look at these quantities. The Seine River in France, they found with their study about 108 particles per cubic meter. And I've got an image of what a cubic meter looks like. That's about 264 gallons in a cubic meter. So that was roughly about 1 particle for every 2.4 gallons. In China, they had much higher rates of 8,000 particles per cubic meter, or about 30 particles for every gallon of water. On the Great Lakes, they found between 2 and 32 particles per cubic meter. And they also did surface sampling where they found about 43,000 particles for every square kilometer of surface area. South Carolina found a big range, anywhere from 100 to 1,500 for particles per square meter, and Chesapeake Bay anywhere from 1 to over 560 grams per kilometer squared. So what you can see from that is they're doing by weight instead of the others by particle pieces. So what I hope you gather from that is some have focused on surface samples, some have focused on all kind of the water flow, and some of it by surface area and some of it by volume. So there's a lot of variation in what's reported out there, and it's kind of trying to make linkages to be able to compare these values. And these microplastics, some of them end up in fish, oysters, crabs that may end up on our dinner plate. There's been some studies in Oregon that had an average of 11 microplastic pieces per oyster. In the Texas Gulf, they found microplastic particles in over almost half of the pinfish. In Canada, in the northern pike, very high percentage, 83%. And in the Mosquito Lagoon in Florida, they had pieces they found in oysters, but also in crabs, very high concentration. So this is a concern again, because this can end up on our plate being consumed by humans. So the goal of our study was to kind of look at how much plastics may be ending up in the Pamlico Sound here via the Neuse River that comes in. Now, we have the Outer Banks band here that prevents a lot of flow exchange between the sound and the open ocean. So that is an opportunity for a lot of things to accumulate in the Pamlico Sound. So we wanted to kind of get a handle on that because this is a very valuable fishery for the state of North Carolina. So our goals are to kind of determine the concentration and loadings of plastics that may be reaching that lower Neuse River that would eventually enter Pamlico Sound, to look at contributions based on the kind of scale of the water body and the land use of the watershed draining to that, and then to identify sampling protocols that really would best fit our waterways considering that size and access and flow of the water bodies, because we're not just looking at the main river or the open ocean moving up into these smaller creeks and streams. So our study has several tasks that we've been working on. First, we are trawling for microplastics at 15 locations around the Neuse River Basin where there's a USGS flow gauging station, so they're measuring water levels and flow amounts at these locations. We are collecting, sorting, and weighing trash from 7 grid samples on creeks in the upper part of the Neuse network. We're conducting visual counts of plastics during high flows at 2 creeks, and then we're also using this litter getter type trash collection system on 2 creeks to collect flow during storm samples. And I'm going to quickly review the work more specifically for each of these tasks. So here's the Neuse River Basin, the outline of that river basin in black here. And here's all 15 sites where we're sampling microplastics. In addition, the ones colored in green circles are the ones where we're doing both microplastics and macroplastic samples, so the larger material. And again, those are at USGS flow gauging stations. So for the microplastic trawling, we first measure velocity at the site with a flow meter. Then we deploy this 300 micron net that's set up with floats on it, so it's capturing at the surface. And we have to get to an area where we have enough flow. And we also measure the flow. This device is there in the net during the trawling period, and we record the time of the trawl. We set our trawl up for about 10 to 20 minutes depending on how much flow is at that site to kind of collect relatively the same volume every time. And then we take our net back and we wash this net down and then concentrate our sample into a small, kind of mason jar type sample. And that is being sent to UNC Wilmington and the Plastics Ocean Project for laboratory analysis. So the laboratory processing, that's being led by Bonnie Monteleone and Pam Seaton. Pam's with UNC Wilmington and Bonnie's with the Plastics Ocean Project. And there's a lot of steps involved with their part of the lab sampling of those. Once we send them those jars that contain a lot of organic matter and potentially plastic particles. The first step is they just visually identify any particles in the sample that appear to be plastics. And then they're having to do a chemical digestion process to remove a lot of organics. In these creeks and rivers, especially during fall and winter, we are picking up tons of debris and leaves, and even though we wash down and remove a lot of that, there's just a lot of organic material that ends up in the sample. So then they go back after that digestion process and recheck for plastic particles, and then they use an FTIR to confirm that any particles they think are plastic, that they're not organic, that they are actually synthetic materials. And FTIR is an infrared spectroscopy procedure that they're using with a very expensive high-tech lab piece of equipment. They tally the total number of pieces of plastic and then measure the total mass and size, which some of these are very tiny, so getting a mass for those tiny particles is not possible in some cases. So this is the kind of ultimate data that we hope to get from them. And we've completed the trawling at about half the sites. We're about to enter our 4th round. So we go bi-monthly for 1 year. So we have 6 visits where we do this trawling at the sites. And then, as I said, next week we will start round 4 of the sampling. So in addition, when we visit the sites every other month, we have set up these grid sampling areas where we have the creek or stream and the floodplain, about 50-foot length of the stream that we sample in. We pre-clean this gridded area, so we've marked it all out, flagged it out. We pre-clean that area, and then we collect all the trash there. And so we actually got everything removed, and then we come back 2 months later and we collect again, and so again every 2 months. So we have this data entry form that we created so we can upload all this material. We sort it by type and do counts. So all the material there, whether it's aluminum, metal, glass, rubber, plastic, we classify all that. And then we bring that material back to NC State University, where we we clean it up, wash it down, dry it, and then we weigh all that material. So here's the scale where we're weighing that material. Okay. And so the other thing we're working on is establishing a database of the weights for the kind of plastic items, so we don't have to weigh every single plastic bottle. Okay, so then we also have this device called the litter getter that we have built. This is a design that we were given permission to build from Osprey Initiative, and I've got their website there. They have a more permanent litter getter they build, and this is kind of their prototype design, and they allowed us to copy that. It's basically like a boom type system that funnels the trash towards the center of the stream, and then there's this floating PVC box with mesh that then it captures the plastic. So it doesn't capture all of it, but we've kind of worked on the design of this and where to install it in the creeks. So then here's all the trash we've collected from one of our sites, which is on NC State University campus. Obviously we have a lot of playing fields, and so we've got softballs and baseballs, and we kind of joke often that these toys and balls are at almost every site we go to clean up or collect trash, that these balls in particular are ubiquitous trash. Also, you can see a number of plastic bottles, oil container, lots of styrofoam pieces and cups and containers as well. We did have to remove these during late fall and winter because they were just filling with organic material. So these have to be set up prior to a storm event. You get them out in the creek. Once it rains, then you go back after and collect all that material after that. We're also doing visual counts, where we're using a method that was published by some Spanish researchers, Gonzalez, Fernandez, and Henke, in 2016. This work is being led by Gloria Putnam, in which you go out during rainfall. So you have to go out, and she's got an app that they created, and you use to kind of quickly tally your trash. It's hard to go out with paper and pen, so this app is very good for setting up some kind of favorites of trash. So in other words, you see lots of plastic bottles, lots of styrofoam pieces, and it grades them by size, and so you can quickly tap on that app. And so you position yourself at a bridge or a certain location where you've got a good view of the water, clear view, and you count for 30 minutes and record all the items that you see by type. So here in this is a count on Crabtree Creek, where we've got an oil container and we've got a plastic bottle that we're floating by during that storm. Our anticipated outcomes are, first, we hope to quantify the microplastic concentrations. So again, by the count and by the weight. Our samples have been surface samples so far, but we're also going to be trawling at different depths at our deeper stations. In the smaller creeks and streams, we're pretty much sampling almost the whole depth profile there. But on the bigger rivers, the Neuse, the Trent, Centennial Creek, we're going to be doing some depth sampling. We know a lot of materials probably floating more on the surface, with the plastics. And then we're also going to estimate the microplastic load to the Pamlico Sound with those concentrations. So we're going to take that concentration data. We've got the flow data. We can use the flow data from the USGS gauge as well as our sample, so we know for a relative volume over time or flow what the concentration is. Extrapolate that using the flow at that station over a 1 year period. And then we can get annual loads of microplastics that would be in the Neuse and heading down to Pamlico Sound. Well, we hope to characterize relative loadings from different land uses. Some of our sites, like Nahunta and Contentnia, have very rural watersheds, mostly agriculture, whereas we have really urban sites in the upper part of the watershed, to see, do we get a difference in microplastics? Also to look at the kind of relationship of macro and microplastics. If there's a link there, perhaps that would give a big incentive or impetus for us to do more about preventing litter from getting in if there's a strong correlation between the two. You know, maybe bags are breaking down, shopping bags or styrofoam cups. So we also want to look at the plastic loading variability over season and flow. Do we see more of it coming in at, you know, higher flows or certain seasons of the year? Maybe it is being the movement of that facilitated with the debris, the organic debris that's coming down. So when you have more organic debris, maybe more plastics are coming down with it. We hope to refine and share the sampling protocols with us. We had a lot of learning. You know, we applied a lot of methods we found in the literature, other studies, and so we hope to be able to recommend that out. There's a lot of municipalities, state agencies that are doing this sampling, and so we want to help with, you know, when you're in a small urban creek versus a deeper river site, here's what we recommend for getting your access, getting your what type of net, everything. We hope to provide tangible data and evidence that will help with education efforts and even, you know, efforts to target at, you know, reducing plastics pollution. So we're working again with Sound Rivers and the Coastal Federation to hopefully share that information. They're doing a lot of educational campaigns on this, and this would give real kind of very tangible, real data to support the need for those changes that they're going to be recommending. So with that, we can have time for any questions. And I just want to show you, here's a styrofoam cup trapped on our Rocky Branch, our NC State University campus creek. These are some rocks that were installed with restoration. And then here's some trash that's accumulating on the dock at the Neuse River. I believe this is the Fort Barnwell site. So we can see that evidence. We've got some very old styrofoam that's breaking down, a bottle, but lots of plastic material and styrofoam pieces that are there. And so we do see that there's certain areas where with the organic matter, a lot of this debris accumulating there.